All right, first talk of the day at 8:30. I'm surprised you guys are here. I sure wouldn't be here if I didn't have to. So yes, this first talk will be like a little historical overview of what has been done in like roughly last 10 years to scale blockchain Web3 to 8 billion users. All right, I'm Kai. I'm mostly into computer security, and for me at least, the most interesting areas for computer security is where security is an enabler, right? So you don't want security to just be an add-on. You want security. You have to enable new products, new services, and I think blockchain is one of these areas where security can still be an enabler. So if you search for like high gas fees or something like that on the internet, you find some pretty funny pictures. So this is an unique swap where we swap like roughly $35 in ETH, and the gas fee is $24. So roughly 80% of the whole value of the transaction is just burned away in gas fees. Here's another example. This is like an $150 swap. These examples are of course cherry-picked, but because the capacity of a blockchain is like at least in the midterm limited. Oh, thanks. It's limited when there's high demand for block space. Transaction fees spike up and they stay there elevated for quite some time. This is not just an annoyance, but this has a real impact on the type of applications you can realize on Web3, right? So this is an example. Here's Friendtech, which has been like super popular a few weeks ago. The basic idea is that this is an on-chain Telegram, but in order to join a channel, you have to like buy your ticket into that. And the ticket is an on-chain object, right? So you have to do an on-chain transaction in order to join, which means that in order to use Friendtech, you have to have a wallet, you have to fund it with ETH, which means if you want to use Friendtech as somebody who's like not a crypto native, that is quite complicated, right? So Friendtech is on Base, so it's fairly good integrated into Coinbase, but still you have to explain to people, okay, you have to like get a Coinbase, buy some ETH, put the ETH that is in your Coinbase account into your Friendtech wallet, and they can use it, right? It's not really very useful, or very easy. Oh, cool. Another example would be Farcaster, which is an on-chain Twitter. So the basic idea is that your account and like all the important information associated with it is an on-chain object. So you are the only person that controls this data, and it's open, right? You can move it to other networks, other implementations, which is pretty cool. But that means that if you want to open an account on, for example, as a Swapcast is like the client for iOS, again, before you see anything, right? Before you see your timeline or can understand like how the product works, who's on there, you're presented with a screen that tells you, hey, please pay $5, right? In order to pay for the gas fee to generate your account. I think Swapcast is pretty much the best implementation of that because it's an app. You can use Apple Pay, right? It's just like one button press away, and then you like have your like in this case gas fee paid. But it's still like hard if you look at least a high friction way to get people onto the product, right? If you compare this with what we have in Web 2, where you first give your product away for free and like get people hooked, and then you have like the upsell. Which makes it way easier to do that instead of like just starting off with it. Okay. Okay. And then you look at the price, right? $5 for a year. If you look at what I can buy on AWS in terms of servers, so the cheapest server or like cheapest VM you can get there is like roughly $20 a year, right? And I would say that one of these VMs can support more than 4 users for a year, right? Obviously, I understand that like doing this on-chain has additional benefits. It's not just some server running somewhere. And I can understand that this costs a bit more, but maybe it doesn't have to cost orders of magnitude more. Okay, so what can we do to make this a bit cheaper, right? And the first thing you have to look at how these blockchains work and why this has to be so expensive. Okay, this is the Web3 track. I assume everybody has like a rough understanding how this blockchain stuff works. I will just like give a short overview. In this case for Bitcoin. So we have a bunch of nodes which are just computers, and they're connected on some kind of network like the internet. And if I want to do something on this network, like for example send money from A to B, I create a new transaction, I sign that transaction, I send it to one of those nodes, and the node would then broadcast this transaction over the network. Each of these nodes receives the transaction, verifies the transaction that the transaction by itself makes sense, and then after all the nodes have received this transaction, the mining process starts. And the mining process is effectively just everybody racing to mine the next block. And this mining process randomly selects one of the winners, who will then produce the next block, which includes my transaction and all the other transactions that has been collected during the time. And then we broadcast the block. Everybody receives the block, everybody verifies the block, and if they're happy with it, the cycle repeats. So if there's a network interruption, blockchains are on the availability side of the cap theorem, so the system continues working, but we have a split world, right? So we have, in this case, 2 worlds, one with 2 nodes, one with 3 nodes, and the mining process in this case will select one of the winners in both worlds. And once this interruption is resolved, they will merge their state, but not in the sense that there's a superset, but one of these states will win. In the case of Bitcoin, will be probably the one with the 3 nodes, because there has been more computational energy put into their state than the other one. Okay, so a few observations here. Every node in the Bitcoin network has to verify every transaction, right? So there's a lot of superfluous verification and computation going on. Also, all the state has to be distributed across the whole network. There are optimizations in order to allow me that after I've verified something, I can at least throw or prune the state, but there has to be at least some nodes in the network that keep the whole state. So in order, when new networks join the network, I can retrieve the whole state and verify it myself. The network has to proceed in lockstep, right? So there's not much parallelization going on. Everybody collects these transactions, they have to be broadcast, then everybody races to mine a new block. Then the block has to be distributed, and then the whole cycle repeats, right? We cannot combine these steps in any way. There's no real parallelization going on, which means that adding nodes to the network doesn't really extend or increases the capacity of the network. It does to some extent, but it trades off pretty fast. It also means that the speed of the network, the capacity of the network, is pretty much limited by the smallest node that is a member of this network. I cannot slow down the network by becoming a node and then just doing less work than I have to. We would just be left behind, but there's no additional benefit from adding larger nodes if there are still smaller nodes in the network. And then there's this mining process, right? This is ironically, of all the inefficiencies I talked about, this is what people concentrate on, is this mining work, which is effectively just busy work in order to randomly select one of these block producers without much synchronization going on. And so the first solution for this mining process was we just stopped doing it. And the idea came up roughly 2011, called proof of stake. We say, okay, instead of having this mining process, we have a different way of synchronization. And in order to prevent people from just generating blocks that are invalid, everybody has to put up some kind of stake, some kind of a fidelity bond that is taken over by the network if they are caught doing something that is against the protocol rules. This was later then formalized into a few blockchain implementations, for example, Algorand or Cardano, where they have even security proofs for the system. But if you look at the system, it pretty much works the same as the proof of work version in Bitcoin. We have a node that generates a transaction. The transaction is broadcast across the network. But then instead of mining something, the algorithm in the proof of stake system has selected one of the block proposers in this case in advance. And the block proposer knows that he's the block proposer, and he will generate a block and broadcast the block over the network, and then everybody can verify that, okay, this block is valid and this block was created by the block proposer. So there's no mining going on, but everything else is still the same. Which means that proof of stake can only, in a very limited way, increase the capacity of a blockchain, right? So the core problem is that we have to distribute this data across the whole network, and everybody has to verify all the transactions. We still have that. There's some alternative, well, not alternative, but improvement on the system called an asynchronous BFT algorithm. Implementation would be, for example, Phantom and Hedera hash graph, where there's a limited amount of parallelization going on. So these blocks and this mining process is one of the main goals is to order all the transactions in a global ordering. With these asynchronous BFTs, I, as a node, collect already transactions and put it into local ordering, and I distribute this local ordering. And then there's some clever graph algorithms going on that combine these local orderings into a global ordering that is then the same across all the nodes. But this is a very limited amount of asynchronicity going on. So you still have blocks, you still have the network pretty much running in lockstep. Okay, so in order to make the system really more efficient, we have to essentially use the blockchain less and build stuff on top of the blockchain, which are like in combined known as layer 2 solutions. Okay, the first layer 2 solution starts with a very simple question. If a tree falls in the forest and nobody's here around to hear it, does it make a sound? Maybe everyone can like think about this for a second. Okay, the blockchain interpretation of this would be, if two people exchange money, why does the whole world need to know, right? I mean, if you look at it from in the physical world, if like two people exchange cash, they don't have to like broadcast this fact to everybody else, right? Maybe you can learn something from that in the blockchain world. And the first idea implementation of this was the Lightning Network for Bitcoin, where we limit the amount of transactions we put onto the blockchain. So we have here Alice with the fancy glasses and Bob in the cat suit, and we have the Bitcoin network over there. And they decide they want to exchange money using the Lightning Network. And what they do is they create something called a funding transaction, where they both put up money, like for example, 1 Bitcoin, and put it in some kind of shared pot. And this funding transaction, that this has to be broadcast on network. So we pay gas fees for that. But what they then can do is exchange the pot of money between them, right? So everybody, both of them put like 1 Bitcoin in, and then one party can pay from this pot the other party, right? And for each of these payments, we create a commitment transaction that effectively allows both parties to receive their money out of this pot, but we don't broadcast this to the Bitcoin network. Just we keep this for ourselves, and only if we want to close the channel, we broadcast the last commitment transaction to the blockchain and tell the blockchain, okay, like this is like how the state is after our commitment transaction. It's like the last known valid state. And this way we can like have exchanges here that don't have to be broadcast to the blockchain. This can be like 1 billion different commitment transactions, but we only broadcast the last. So we only have like 2 fees we have to pay. Once to set up this channel, what they call it, and once to close it. I would like super briefly tell you how this works, because I think it's pretty neat. The basic idea is you have this funding transaction here where we start off with, and then we have these commitment transactions we create, and these spend from the funding transaction, right? So everybody puts like 1 Bitcoin in, and we create commitment transactions. There are always 2 of them. So one of them is Alice commitment transaction that she can send to the blockchain, and then one is from Bob. And Alice transaction just says, okay, Bob gets his money back immediately, but Alice has to wait some kind of time, and the time is measured in blocks produced. And then there's the mirror transaction for Bob, right? So Bob's transaction, the transaction Bob can send to the blockchain, Bob has to wait for his money, but Alice gets her money immediately. And in order to spend this money or do a transaction on this pot, you just create a new set of commitment transactions. So let's say we pay 0.2 Bitcoin from Alice to Bob, then we create a new pair of these transactions. In this case, we have one where Alice has 0.8 and Bob gets 1.2, and again there are pairs of them that each of those can close the channel, but depending on who sends it, then they have to wait and the other party gets the money immediately. And we also create an revocation transaction for the previous committed transaction. I will explain this a bit later. So in the best case, if everybody is correctly executing the protocol, we have this funding transaction that is committed to the blockchain, and then we have the last commitment transaction. So both put in 1 Bitcoin, and then later we close the channel with the updated balances. And it doesn't really matter, right? Alice can send a transaction, or Bob doesn't change the fact. But now is of course the question: Alice could try to defraud Bob, right, by sending the old commitment transaction where she still has 1 Bitcoin instead of 0.8. And this is what this revocation transaction is for. What Bob can do is he can monitor the blockchain and can see, hey, wait a second, Alice sent this revoked commitment transaction to the blockchain, and then you can use this revocation transaction to steal Alice's money, right? So because Alice still has to wait a few blocks before she gets the money out of this transaction, Bob can use the other transaction to steal the money before this happens, and effectively punish Alice for violating the protocol. So in conclusion, the basic idea is, first, we limit the amount of interaction of transactions we send to the blockchain. Instead, we have a local history of what has happened that we can then later use to update the blockchain, or in the case there's some kind of fraud, to prove that we are the party that followed the protocol correctly and the other party violated it. This kind of mirrors the clearing and settlement system we have in TradFi, right? So when you pay something with a credit card, it first goes through clearing, which takes a few seconds. But in order for the transaction to settle, for the money to actually go from your bank account to the vendor's bank account, this takes like days to weeks. And during this time, the transaction is just exists as some database entry in the clearinghouse. That's all cool, right? We have solved the problem. The problem is it is unclear how to extend this to something that is not a payment, right? So the real benefit of blockchain is that you can have general computation on them, right? For example, Ethereum has a smart contract platform. How to do this system with something that is like just a program instead of just a payment was an open question for a long time. Historically, the next idea were first packed side chains and later then refined into plasma chains, where the idea is you just have multiple blockchains with different trade-offs. So in this case, we have Ethereum, which is our slow and expensive, but very decentralized and secure chain, called the root chain in this context. And then we have the Polygon here as example. There are other implementations, but Polygon is like the canonical example of this. That is a smaller chain with less decentralization and lower gas fees, but also lower security, presumably. And the idea is that the plasma chain receives the state from the root chain. So the plasma chain always knows what's the latest block in the root chain. Then the plasma chain runs its own consensus algorithm, which is tuned towards speed and low fees. So for example, you could just have lower decentralization, less blocks, less nodes that have higher capacity, or you have something like proof authority where we say, okay, all the participants in this like smaller blockchain are known and we trust them, so we can lower the requirements on verification for transactions. And it's not like everybody can join that network. It doesn't really matter what it is, it just has to be faster than what we do on the root chain. And then we commit these blocks we create on this plasma chain and send it back to a root chain as some kind of commitment. Okay, we say, okay, this is a new block. we put this into root chain, and then this block is like settled. There's no verification done here really. It's just we put it in there, and then we say, okay, that's the last state. So basic idea is, right, we have like a high security, high decentralization, high fee system here in our root chain, and then we have the low security, lower decentralization, but higher throughput and lower fees chain on the other side. And the basic idea is you can use the plasma chain to pay for your coffee, but you can use the root chain to pay for your house, and you can have these different trade-offs and decide which one is currently the better protocol to use. The whole reason why we connect these chains together is so we can move assets between them automatically, right? Bob can deposit some kind of asset, for example ETH, into some smart contract on the root chain. This state update is sent to the plasma chain. Plasma chain sees, oh, okay, somebody has deposited something, and then the plasma chain can credit you that asset or a mirrored version of this asset on the plasma chain. Then you can use that, and the plasma chain can then burn it, like send it to some address where there's no private key known for, and then later there can be proof submitted to the root chain. So yes, this has been burned on the plasma chain, so you can retrieve it from the smart contract on the root chain. Okay, this allows us to have different blockchains with different trade-offs, but doesn't solve the core problem, right? We still have this, these are still blockchains, right? We still do redundant computation. We still have to distribute the whole state across the whole network. So the core inefficiencies are not really solved. The next idea was to actually do things off the chain using something called a rollup. There are two types of rollups. There are the optimistic ones and the zero knowledge ones. Because Arbitrum, one of our sponsors here, is an optimistic rollup, and they paid for my breakfast. We're going to start with them. So in the optimistic rollup version, we again have a blockchain that we assume is safe and secure, and then we have off-chain components. And the off-chain component here means it's just some server running somewhere by some guy that we don't really trust. We know it's there, and we can verify what they do. But we don't have to trust them. And there are two of them. There's the sequencer, sometimes also called the batcher, and then there's the state function or state transitioning function or a proposer. And the basic idea is, in order to use the rollup, you send your transactions to the sequencer, and the sequencer batches them up and commits them on as one block into the like underlying blockchain. And that's the first way you can save on transaction fees, right? Instead of everybody submitting their transaction to the blockchain and paying the fee, you do it once in one batch, right? Obviously, we don't want to. Oh, right. So, and then we have the state function that reads these committed transactions plus the previous state and computes the next state. And again, the state is committed to the underlying blockchain. So, of course, we don't want to have to trust these systems. So, if the sequencer, for example, is down or it just refuses to accept your transaction, everybody has still the option to directly submit their transaction to the smart contract on the blockchain. This obviously it's more expensive, right? Because you have to pay the gas fees in this case, but you cannot be censored by the sequencer. Okay, but what about the state transitioning function, right? This is way more important. What if this thing does something wrong and, for example, includes my transaction but doesn't execute it or executes it wrong? So if you look at the state transitioning function, right, it's pretty simple. We have the list of transactions that goes in as input. We have the previous state that goes in. And then we have the function in the middle, which is known, right? Everybody knows the state transitioning function. It's part of the system, and it's deterministic. So what I can do if I have the feeling that the off-chain version of the state transitioning function did something wrong, I can challenge that. So I have to put up a bond first in order to make the system not abusable. But then you can say, wait a second, this last state that you produced, I think this is wrong. This should be the state. So put up your alternative interpretation of the bond. And then what we do is effectively run the state transitioning function on chain. So the whole thing that has been done off-chain for efficiency reason, we do it once on-chain for this particular state transition. This is a gross simplification of what we actually do. So in reality, there's a game that runs before that where I, in the off-chain state transitioning function, figure out, okay, which is the exact instruction that we disagree on, and we only run this instruction on the blockchain. But this is just an optimization, right? From a conceptual point of view, you can imagine, okay, we run this transitioning function on-chain once, because the assumption is running it on-chain is something that nobody else can manipulate. And once we decided, okay, who was right here, we can continue with the off-chain computation. So these are the optimistic rollups, right? We assume the off-chain components are truthful to their words, right? They do everything right, but we leave the door open to challenge this. The other implementation would be a pessimistic rollup, where we eagerly verify each of these new states. I'm only going to explain this like a little bit here, very brief, because yesterday we had a talk from Leo, right? That all explained CK in very much detail, so I guess you guys are all experts now. But the basic idea is we still have a sequencer, which is also off-chain, but instead of this block proposer, we have a prover. And the prover gets the transaction set from the sequencer and does the state transitioning, computes the next state, but it also computes a cryptographic proof. And this proof can be verified and make sure that the prover has followed this state transitioning protocol correctly, right? And then the smart contract can verify that. And if the proof is correct, it accepts the next state and everything's fine. Okay, why don't we always do that, right? I mean, isn't it way easier to do this like on-chain fraud-proof thing with the state transitioning function, and with that we have in the optimistic rollups? Well, so collecting enough transactions for the next state takes the sequencer maybe a minute. Creating this cryptographic proof takes an hour, 2 hours. So it's very computational intensive, and that's why we can fix this problem a bit using just more provers, right? Parallelizing the operation, but it's a very expensive operation, and this is why, at least for the CK protocols we have now, we are just on the edge of something that's actually practical. So there's still a lot of research going into these things, but they seem to be like the best way forward here. Okay, last one, data availability. So if you look at back at the rollups, we use rollups for two things, right? We use them for execution, doing this fraud-proof thing, or doing the CK proof verification, and for just bulk data storage, right? For the list of transactions, we dump them in there, not really to store it, but to just have a commitment to this transaction, and have a place where we can store them where it cannot be deleted later, right? Because if you want to do this fraud-proof thing, you have to be able to retrieve the previous data. And Ethereum wasn't really built to be a bulk data storage. I will skip this to save a bit of time, but the basic idea is there have been some improvements like mid-March this year, having a new transaction type, which makes it a bit cheaper to have this data. Why? So we, instead of packing the data in transaction, we just have as an attached thing, and we only have some commitment that's in the transaction, which makes the whole thing like 1 order of magnitude cheaper, roughly. Well, at least it did until like a few days ago. So this is the graph of the fees we have to pay for this new transaction type. So it stayed at effectively 0 for a long time, but then later people figured out, hey, we can use this for other stuff, and suddenly we're on the upside for the blob fees too. So this doesn't seem to be like a long-term solution here. What is probably more of a long-term solution is to have something called the data availability layer, where we have a dedicated blockchain that is only there for data storage. So instead of having a smart contract platform in there and being able to execute whatever program you want to, these kinds of blockchains, they only receive messages. Messages have a namespace. This is what they are color-coded here. And then they have some uninterpreted bulk data attached to it that we don't really, the blockchain doesn't really care about it. And what we can later do is to use that as data storage for these rollups, right? So in this optimistic rollup, for example, you had the sequence that it would like just dump the transaction list onto this data availability layer, and only the important things like the next date maybe would be put onto the Ethereum blockchain, saving a lot of transaction fees and making the system a lot cheaper. All right, in conclusion. So we started off with improving on the consensus algorithm itself, right? Going from proof of work to proof of stake, trying to make the proof of stake mechanism as efficient as possible. But later we went to more chains, right? Having different trade-offs for different chains, and trying to make the system a bit more efficient this way. And then we later moved on to off-chain components, right? We have this batching and delay consensus mechanism that you have with rollups. And at least for the future, it seems to be that we're going towards the CK solution, right? Because the CK solution solves the two big problems, right? We first can generate a proof that some kind of off-chain components followed the protocol correctly, right? We do only the verification on-chain. And second, because of the zero-knowledge properties, you can have inputs into your smart contracts that you don't have to reveal, right? So you can even process private data on the blockchain, even though everybody can see the state. Not everyone can see all your inputs. And that's it. Thank you very much.